So, welcome again to this session. We are now ready to start. The presenter is Dr. Everton Cavalcante. And Dr. Cavalcante, the floor is yours. If you want to see.
Yeah, because the camera is here, I think. Where my the camera is there?
Yes.
Okay. So I can be standby.
As you like.
Okay. Thank you. So I think that everyone is hearing me. That's great. So as introduced, my name is Everton Cavalcante. I'm a professor at the Federal University of Rio Grande do Norte in Brazil. I'm here in Malaga with also Professor Thais Batista, is one of the co-authors of this paper. And together with Tiago Vinicius Remiro da Costa, we are going to present our paper. It's entitled Big Data Soft Architectures, an updated review. This work has been motivated with the prominence of big data systems nowadays. These systems are well characterized by the so-called 5V of data, and these kind of systems have many other intrinsic functionalities and characteristics that require having soft architectures to meet both functional and non-functional requirements for these systems. So soft architectures in general, they are well known for being the backbone of any successful software system. And hence, this applies to big data software systems too. And this element of soft architectures are quite important to aggregate the constituent elements that are going to provide the functionalities for these systems, including data extraction, processing, integration, analysis, and visualization. But soft architectures go beyond these functionalities because they contribute to meet important quality requirements for these systems. Because decisions made at the soft architecture level can impact indirectly and directly too the quality attributes such as scalability, availability, high performance that are quite important for big data systems. But why we are motivated to this work? We know that big data systems are relevant nowadays, and soft architectures are relevant to the success of these systems. So it may be worth investigating the literature to understand the characteristics of big data soft architectures and to understand what are the main elements and the main quality requirements that need to be addressed at the architectural level and how we can facilitate the better development of this kind of systems. We are aware that there are already existing secondary studies in the literature about big data soft architectures, but all of this work consider only primary studies published until 2017. So there are it's a body of work that is 5 years old now, and recent work has been published since then. Despite these papers, these studies have followed a systematic methodology in terms of how we can search for, select, and analyze these studies. The existing studies miss this time window of 5 years now. And another motivation for this work is that recent concepts associated with big data systems are not covered by these studies. For example, data lake in the sense of having a repository of data and systems, people, organizations can explore this data in that data lake, and also data platforms that are the infrastructure that facilitates the development and the application of data for systems, for people, and so on. So these concepts of data lake and data platform that are relevant for big data systems, they are not covered by the existing work. So in this work, we decided to update the literature covering the last 5 years because, okay, we already have a panorama of the literature until 2017. So it doesn't make any sense covering the whole literature. So we can focus on the most recent literature because to having another literature review covering the whole existing works is not worth of time and effort. So we decided to cover only the last 5 years to update one of the existing secondary studies, and we performed a systematic mapping study on the literature to collect, select, and analyze the primary studies published since 2017. So our main purpose with this study is that expecting the results to contribute to better design soft architectures for big data systems, including understanding which are the architectural modules, and the architectural requirements that are relevant for big data systems. So, but before carrying out the systematic mapping, we need to analyze if this systematic mapping is worth investing. So there is a work from Mendes et al. Published 2 years ago. Yeah. They proposed adopting a decision framework to guide the decision about updating or not a systematic literature review in software engineering. So they adapted an existing framework from the medicine from Gartner et al. And this framework consists of 3 main steps. We need to assess the currency of the topic investigated in the literature. We need to identify if new methods and studies are available to decide if this body of work is worth investigating, and we need to assess the effect of updating the review. So if the results of the updated review will be relevant enough to justify the effort to apply to the systematic literature review. So we started answering the questions posed by this framework. So we identify that big data systems represent a recent topic of work of investigating. We saw that the existing work has followed a systematic valid method, and so we identified that new studies are relevant to be analyzed in another systematic literature review or systematic mapping study. And we hypothesized that updating the review could aggregate new information about the understanding of big data systems. So based on these answers, we had confidence. Okay, we may proceed with updating a systematic literature review. So this is the method that we followed. We followed guidelines that are well established in literature about systematic literature review. So we planned, resulted in a protocol that guided all of the execution of the systematic mapping study. And then with the studies once collected and analyzed, we reported the results in this paper. So these are the research questions that we were interested in too. So we were interested about identifying the main requirements, the main quality requirements for big data systems at the architectural level. We were also interested about identifying the main modules or components for big data systems and their soft architectures, and identifying how we can map these requirements and architectural models to reference architectures for big data systems. So these are the three research questions that we were interested about in this systematic mapping study. As such a strategy, we performed an automatic search process in the last quarter of 2021. More precisely, yeah, the last update was in December, so it covers the whole year of 2021. And we carry out the search process considering 6 electronic databases that are quite used in computer science and engineering. And we consider that this search string, so addressing big data or data lake or data platform, and soft architecture or reference architecture or reference model. So with this search string, we are expected to collect papers addressing soft architectures or reference architectures for big data systems. And the automatic search process resulted in a total of 1,378 studies where we recall the example. Of course, there are duplicates between the databases. So we made a first filtering to remove duplicated studies, and we applied some selection criteria on the title abstract of keywords. Those selection criteria consisted of checking if the paper have the potential to, or is quite or somewhat related to big data soft architectures. After that, we applied the same selection criteria in the full text. So we read all of the 32 studies and checked if the paper is actually related to big data soft architectures. And this process resulted in a set of 23 primary studies that we analyzed as relevant to this study. So, answering the research questions, we identified 11 quality requirements for big data systems.
So we can interrupt you. We have a problem online. So we
okay.
interrupt you, as you can see. And please, everyone, you should not share your screen. You are actually sharing, you are currently sharing your screen. Sorry. Okay, yes. You should not share, please. Exit the sharing mode.
Okay.
Okay, thank you. Sorry for the interruption.
As I was saying, from the analysis of the primary studies, we identified 11 quality requirements as relevant for big data systems. These are the frequency of appearance of the 11 requirements. It's important to say that 8 of these requirements, so in the left side, they were already identified in primaries in other secondary studies. But we identified 3 additional requirements, more precisely usability, suitability, and maintainability. So it's important to say that the most frequent requirements were scalability, security, availability, and maintainability, as they directly affect big data systems. For example, it's important to say that big data systems, they handle a huge volume of data, so scalability is quite important. It's also important to make this data available, and another concern is security, because, well, people are more and more concerned about the security and privacy of data in the last years. So this is why security has appeared as one of the most frequent requirements of among these ones. And maintainability is also important because making a separation of concerns through modules and layers can improve the maintainability of the systems and also the stability of big data systems. As answering the second research question, we identified 6 architectural modules for big data systems. These modules are quite related to the main functionalities expected for any big data system. For example, have the integration, storage, and analytics of this data and visualizing this data. But we identified an additional requirement, an additional module that is related to data governance. That's related to the ensuring quality and security of data in terms of establishing roles and policies to assure that these data have quality, integrity, and security. So any big data system should be following, of course, our reference architecture, may follow and may aggregate these different architectural modules. And talking about reference architectures in the third research question, our main interest about looking at reference architectures for big data systems is that the development of these systems can be well guided by these reference architectures. So a reference architecture establishes the main foundations in terms of components and quality requirements that need to be addressed by any system following the reference architecture. So a reference architecture for big data systems will establish it, okay, I'm going to develop a new big data system. Which are the modules or the components that need to be encompassed in these systems? Or which are the quality requirements that I need to be worried about? So our reference architecture contains all of these informations as main building blocks. We analyzed it, we identified some reference architectures for big data systems, and we saw that data analytics, storage, and data governance are the main building blocks in those reference architectures. But seeing the modules that we identified and the requirements that we identified, we saw that most of the existing proposals do not fully meet these modules and requirements. And we also saw that in some proposals, data integration and storage, they are blended in a single module, and this may bring some problems. And we also, for example, in terms of separation of concern, if you decide to change the technology for storage, this will affect the data integration component, and this can hamper the evolution and the maintainability of these systems. To conclude, the findings of this work confirm existing findings in the literature about soft architectures for big data systems. As we said, we identified 11 requirements. 8 of these requirements were already saw in the literature, but we brought 3 new additional requirements: usability, suitability, and maintainability. Moreover, we identified 6 architectural modules relevant to big data systems in these architectures. But about these modules, data governance arose as a new module. We also identified that the existing studies have growing attention to security and privacy, because in the last 2 or 4 years, we saw the enforcement of new regulations about data. For example, the GDPR here in Europe, CCPA in the USA, and LGPD in Brazil, just 2 years ago. So as systems need to comply with these regulations, big data systems need to follow the establishments from these regulations. And also, privacy and security on data has also drawn attention because of the incidents that we are witnessing in these last years and the threats and misuse of data. So data privacy and security are requirements that are calling more and more attention. And we also concluded that big data systems nowadays, they fail to follow a systematic process to design reference architectures. So in our research agenda, we envision to establish or to follow a reference architecture process to propose a reference architecture for big data systems, because we identified that many of the existing reference architectures, they are proposed without following a systematic process. So the architectures are made in an ad hoc way, and this may, of course, hamper the good development of these systems. So this is everything for today. I thank you for your attention here, and these are our contacts. So feel free to make your questions here or later. And thank you very much for your attention and the support.
Thank you very much for your very interesting presentation. Congratulations.
I'm not sure if people in the audience have any questions.
Are there any questions from our in-presence or from our virtual audience?
I'm not sure if you have written something.
No.
Oh,
so maybe we can also get some questions later in this session.
Yes.
Thank you again for your presentation. And
can you remove?
Yes, please. The next paper, the next contribution is entitled Scalable Solution for the Anonymization of Big Data, Spatial Temporal Trajectories. It is a virtual presentation, and the author is Dr. Jalel Eddin Agilawi. Are you here?
Hello.
Hello?
Yeah, I am here, so I will share my screen.
Yes, you can share your screen and start with your presentation. The floor is yours.
Okay, thank you. The screen is coming. So please, are you seeing my presentation?
We can see your screen and we can hear you. The floor is yours.
Okay. So I will present you my paper entitled Scalable Solution for the Anonymization of Big Data Spatio-Temporal Trajectories, which is done in Telecom Polytech in collaboration with the Orange Group. So for agenda, we will have introduction, motivation of project, contribution, and we will share results, and we will finish with the conclusion and perspectives. So this project is done in Orange, which is aligned with RGPD rules, and there is a team to try to analyze spatio-temporal trajectories for mobile users in order to not be able to re-identify users' mobilities. So in general, we have data collection in a cellular network, which are divided in 4 groups, which are CDR, or call detail record, UPT or user plan, traffic data, control plane, traffic data and radio measurement reports data. So this table shows the different collection in cellular networks and the main criteria, which are data fields, location granularity, sampling rate, and participated users. So data are faced to principal attacks by inference, which is defined as which deal with location privacy, which is defined as the ability to prevent unwanted entities from knowing their past, present, and future location. There is a taxonomy or a tree of the main point of interest, which are to predict movements, link records, learn semantic movement, or discovery of social links, or predict demographic attributes. There is an existing taxonomy of related work, which are under mobile traffic analysis. So we find social analysis, mobility analysis, and network analysis. So for our work, we will be interested in mobility analysis. When we have human mobility, fundamentals law, and models. Also, we find transportation system and validation. So in literature, there is some public challenges in telecommunication industry, which are, for example, data for development, which is launched by Orange, or big data, which is launched by Telecom Italia. So our solution is based on big data stack. So there is a team of data scientists who have developed a proof of concept to anonymize data based on meta-heuristic algorithm, which I have migrated to Spark and Scala for scalability reasons. So the reference architecture of our project is illustrated by this figure. So we have data source, and after that we have data ingestion. There is a computation engine. We have worked our research as a batch data, and also we have we deal with cluster management and API service in order to expose our data and visualize them. So for communication architecture, so we have two programs. This is existing program, which is a merging program. I have developed the Cartesian program in order to limitate the computation space. After that, we have data fusion standard and data export, which is done with Scoop as an ULT for streaming data. And in order to expose geospatial anonymization data for users. So for the function architecture, we have data source, which are based on CDR, which are files which record different user trajectories we pre-process them in order to clean and aggregate them. After that, this model of optimal merging computation will be executed in order to have a generalized trajectory which combine a subset of trajectories which have the same shape. And the main contribution of this work is to extend this model by filtered Cartesian computing model in order to optimize the processing to have running time gains. So there is the Camer's algorithm for trajectories generalization, which is developed by our collaborators. And this algorithm allows to combine a subset of trajectories by one trajectories after computing cost of fission of merging between trajectories. So filtered Cartesian computing algorithm is proposed in order to optimize treatment, which is based on metaheuristic algorithm, notably machine learning algorithm to not surpass a certain threshold for computing merging costs. So they see the fission cost matrix of trajectories. So the existing developed system is a very time-consuming system, and we have tried to optimize processing time by reducing the matrix cost space of computing, and we have gained in terms of running time. So there is the assessment of the existing Camer's algorithm. It illustrates the number of users and the running time. So for our work, we have developed a spatio-temporal big data trajectories platform. It is based on Spark and Scala. It is dedicated to anonymize trajectories. So we have Camer's algorithm, and we have extended it by filtered Cartesian computing algorithm. In perspective, we count to establish tests on large data on the internal cluster and measure the time saving of the filtered Cartesian product algorithm. And thank you for your attention.
Thank you very much for your presentation. Are there any questions from the audience? I guess no. So we can maybe we can go on with the next and last presenter for this session, and the last paper, the last contribution is entitled "A Deep Learning Model for Mammography Mass Detection Using Mosaic and Reconstructed Multi-Channel Images." It will be a virtual presentation. The authors of this contribution are Nada Hassan, Safwat Ahmad, and Khaled Mahar. The presenter, I guess, is Professor Hassan. So if you are ready, you can share your screen and the floor is yours.
Okay, I will share my screen now.
Professor Hassan, can you hear
Here
us?
is Mokla.
Okay,
Yeah,
we can hear you.
Hear me? You are hearing me, right?
We can hear you, but we can't see your screen.
I'm
So
trying to share my screen, but I don't know why the sharing is failed.
sorry, I didn't understand.
I'm trying to share my screen, but there is a message that telling me that sharing is failed.
Okay.
I cannot share. There's something that went wrong.
May I ask you which browser are you using?
Chrome.
Okay. Actually, I don't know which should be or which could be the reason of this issue. So maybe you can try
Another
restart the
browser?
system, or at least disconnect and then reconnect again. Maybe
Okay,
we
I
are
will try.
here. We'll be waiting.
Okay, I will try from another browser. Okay.
Okay. Thank you.
Welcome.
Professor Hassan, welcome back.
Welcome. I'm trying to share right now.
Okay, now we can see your screen.
Okay. Great. Can you see the presentation?
Yes, we can see the presentation.
Okay. I will start.
The floor is
Okay.
yours.
Thank you. I'm Nada Hassan, and I'm here to present our work in the paper entitled The Deep Learning Model for Mammography Mass Detection using Mosaic and Reconstructed images. Here is our agenda. We will start with problem statement, motivations, and contribution-related work, then experimental settings, including dataset, preprocessing and augmentation, experiment design, and our experimental results and discussion, then finally conclusion and future work. Breast cancer is considered as the most type of cancer that hits women around the world. And this can be clearly seen from this chart, as it almost represents the highest incidence and mortality rate according to the Global Cancer Statistics 2020. And the clinical studies prove that the early detection of breast cancer can enhance the survival rate from this type of cancer. And regular screening detection. Mammogram is considered as one of the most usually used techniques in this screening. So in this work, we are focusing on detecting masses within the mammogram images. With the rapid growth in the computer vision section or sector and machine learning techniques, the CAT systems become more accurate and start to act as a second opinion for radiologists. So in this paper, we are mainly contributed with some points Firstly, we are working on enhancing the appearance of the breast masses and the tissues by reconstructing the mammographic images into multi-channel colored images. Then we evaluated the impact of this step on our model, which is based on YOLO V4. Also, we are utilizing and evaluating the impact of using new augmentation techniques like Mosaic and mix-up with conventional augmentation techniques with different combination in this work. And finally, we evaluated the generalization of our model on unseen images from other data sets that were obtained from different scanners. Okay, briefly, in the related work, here is some of the related work in our paper. We can see here there are different techniques that were adopted recently, which is based on deep learning detection mainly. And they showed very promising results, as we can see from there. But there is a research gap over these reviewed researches, that the majority of these research didn't focus too much on enhancing the quality of the image itself before training. Also, the detection of small masses and detection of masses generally within the denser breast tissues are still considered as open challenges. So in our model, we are proposing a model based on YOLO with utilizing Mosaic and mix-up augmentation techniques. YOLO was used for mass detection and classification in mammogram images, and Mosaic and mix-up for augmentation or augmented data to increase the size of that and to investigate their impact or effect on the detection of the existing masses within the mammogram. Briefly, we can describe YOLO V4 as a single-shot detector, which takes the input image and into S by S grid cells. Then for each grid cells, grid cell, there are bounding boxes that are generated, and each cell is considered to be responsible for detecting the object if it contains the center of the cell contains the object inside it. And the risk confidence scores are calculated for each bounding box to calculate the likelihood that this cell contains an object and overlapping, and this bounding box overlapping with ground truth. After that, there is a non-maximum suppression algorithm was implemented to eliminate the bounding boxes with lower confidence score, and the overlapped bounding boxes also. Okay. Also, we adopted Mosaic and mix-up in our experiments. Mosaic is mainly an algorithm that combined 4 of the training images into one image with the original size of single image. So the objects in each image of the 4 are appearing on smaller scale, and this enhances the detection of small masses, by the way. The other technique is mix-up, which blends the features of 2 images in one image with their corresponding labels from the training set. Here is our experimental settings. We use the 3 different data sets. The first one, DDSM, and we used very few images from it to test our model. And we conducted mainly our experiments on impressed dataset and MIAS dataset. Each one has different type of mammography images based on the used scanner. And we are using from impressed 107 images from out of 410 because we are focusing only on the images with masses only in this work. Also, we used 55 images from MIAS out of 322. Okay. The images in impressed and CPIS DDSM are in DICOM format, while the MIAS in BMG format. We converted them to JPEG and scaled the images into 8 bits. Then we extracted the breast region using also thresholding and Gaussian filter. After that, we normalized the pixels intensity to be in the range of between 0 and 255. The normalized image then used to apply that clip limit adaptive histogram equalization at two different clip limits, and then finally we merged the normalized image with the images that were produced from the clip limit adaptive histogram equalization step. And we can see here, this is the original image, and this is its corresponding reconstructed multi-channel image. Okay, then we augmented the data set to increase its size because the size of the data set is very small. So we applied firstly on the testing and the training set conventional or traditional augmentation techniques like flapping, rotation, and blurring, something like that. Then we applied through the training phase mosaic and mix-up augmentation techniques on the training set only. And we can see there how mosaic combines the four images with each other. Okay, we designed our experiments to conduct 5 experiments. The first one, YOLO V4, on all the experiments, we will find the main model that we used, YOLO V4, and the combination of the augmentation techniques will differ. So the first one, we use conventional augmentation with mosaic normalized images. The second one, conventional augmentation mosaic multi-channel images. The third one, conventional augmentation multi-channel images. And the fourth one, conventional augmentation with mix-up and multi-channel images. And the fifth one, conventional augmentation with mosaic and mix-up plus multi-channel images. Here is the results for experiment 1 and 2. And these experiments were mainly focused on evaluate the effect of the step of pre-processing or the reconstructed images. As you can see from this chart, that the multi-channel images with mosaic gives the higher scores in terms of mean average precision and F1 score, recall, and precision. And also, if we look at this table, we can see clearly that the model were able to distinguish better between the benign and malignant masses. Okay, here's the results for conducting 4 experiments on MPREST, and we conducted the same experiments on four experiments. The first one was conventional augmentation with mosaic, second one conventional with mix-up, augmentation with mosaic only gave the best results. Also, we can see that the true positive and false positive and false negative enhanced, and the false negative rate also enhanced a lot with the conventional augmentation with mosaic. And the same for distinguishing between the benign and malignant masses. Here's the results for the same 4 trials that we mentioned before on MIAS. And also we can see that conventional augmentation with mosaic achieves the best results. However, conventional augmentation with mosaic and mix-up showed better results in terms of precision. But in all other terms, conventional augmentation with mosaic showed the best scores. For further investigation, we tested 21 unseen images from MIAS on the model that we trained on MPREST only, MPREST mammograms only, and it gives us these results as we can see here. The mean average precision 71.93, which is very not good. And it's important to note that MIAS dataset is composed of screening film mammography images, which has lower quality than the images that composed of impressed, which is full field digital mammography images. And this can clarify why we obtain these results as a model trained on full field digital mammography images and tested on SVM images, which have lower quality. However, we can see that in the other results, when we trained the model with MIAS only and tested it, it gets good results, by the way. For more investigation and to test the generalization of the model, we selected randomly images from CPIS DDSM and from MIAS dataset to test them on the model that trained on impressed with Mosaic. And we can see clearly from this diagram that the model succeeded almost to detect all the masses that are existing in the mammograms, except for this, by the way, are the detected masses, and this is the ground truth. The first two lines for DDSM and the other for MIAS. We can see here there is extra detected mass, which is not exist in the ground truth, but rather other than that, the model succeeds in detecting all the existing masses. Okay, our observations from these experiments that the multi-channel images or the pre-processing step enhances significantly the mean average precision by almost 10% and the sensitivity by almost 7%. Also, it improves the classification accuracy for each class, the benign and the malignant. The Mosaic improves the number of true positive and false negative of mass detection, whether for impressed or MIAS, as the Mosaic allows the model to learn the masses at different scales and different contexts. The mix-up and Mosaic together show competitive performance. They achieved almost the same sensitivity score as Mosaic, however, it showed lower mean average precision than Mosaic only, and this perhaps happened because the techniques that adopted in mix-up, as mix-up mainly it changes the pixel values of the mammogram images when mixing up two images. This perhaps affects the appearance of the mass shape and the surrounding tissues, and accordingly the detection task. From the results, we can clearly observe that full field digital mammography images has better accuracy in detecting breast cancer than screening film mammography images. The training with Mosaic combination and conventional augmentation allowed for better generalization rather than the other combinations. The model enhances the classification results, and the main advantage of Mosaic, especially in these experiments over the other evaluated techniques, is mainly in producing new images at different and smaller scales, which helped a lot in detecting the small masses. Okay, in conclusion, we can say that we proposed a model that based on YOLO V4 with Mosaic and multi-channel images that was able to achieve mean average precision of 99.3 and false negative rate of 0.06. The model was able to detect the masses with different sizes when tested on unseen images from other data sets, which means that model can be more generalized. And we are intended in the future work to extend this work to detect other abnormalities in the mammograms and to evaluate this work on other data sets. And thank you. If anyone has any question.
Thank you for your presentation and congratulations for your work. Are there any questions from the audience, from the room? No, I guess there are no questions nor comments. So I want to thank all the participants, all the speakers. I want to congratulate all the participants for their outstanding work. and I leave you to the next session that will start at 4:20. So again, thank you all. Thank you for your participation and enjoy the ICCSA conference. Thank you very much.
Thank you for you. Thank you.
tutti appunto non sono d'accordo, sono invece
Okay, so can you hear me? Is everything all right? Hopefully from the audience. Okay, so I start the session 7B, general track 5. So first presenter is not here, so I'll go with the second one from Madikana Sediela. Okay, yeah, please come. I'm starting to share the screen. So his title is Impact of Radio Map Size on Indoor Localization Accuracy. Please. Sponsors. Yes, continue.
Okay, good day, everyone. My name is Madikana Sediela. I'll be presenting a topic, the impact of radio map size on indoor localization accuracy. The paper was written by myself and my co-authors, which is Dr. Moses El Radeve and Professor Ugute Paul Kugera. So the outline of our presentation is introduction, aim of the research, methodology, and under methodology we will discuss the system architecture, radio map generation, experimentation and results, and finally the conclusion. So under the introduction, the whole topic falls under location-based services, which provide the useful information about a person's current position, including their action and behaviors. These location-based service applications, they are divided into indoor and outdoor applications. And we know that in an outdoor environment, the global positioning system, the GPS, is the most successful one. However, when you move in an indoor environment, GPS faces challenges because of multipath effects, interference, and shadowing. So to alleviate GPS in an indoor environment, the indoor positioning system proposes some of the technologies such as Wi-Fi and Bluetooth to alleviate GPS indoor. So these technologies like Bluetooth and Wi-Fi, they are usually deployed with the fingerprinting algorithm. And this fingerprinting algorithm is divided into two phases, which is the online phase and the offline phase. During the offline phase, that's where the data generation is performed, where we collect the measurements of signal strengths from the transmitter devices. And during the online phase, that's when the localization takes place. So, yeah, as I already mentioned, that during the offline phase, we collect what we call the RSSI, which is basically what we will use to estimate the location of a transmitter device in an online phase. So we deploy the machine learning algorithms during the online phase to localize these transmitter devices. So the aim of the research. So in this study, we investigate the impact of the radio map size and correct RSSI measurements to simulate the effect of the outcome of the predictive model. So we decided to collect data in an incremental pattern. So we have 3 scenarios that we will discuss in detail as we go along. So we will finally provide a comparative performance of the models as the dataset increases. Methodology. So in order to achieve our goal, we have developed a system that we named IMSIS, which was designed following the fingerprinting algorithm. And the tools that we used to develop this application, we used Java and on Android Studio platform, and for designing we used XML. And then the system architecture of our IMSIs. So as presented in the image, it is made up of two phases, which is the online phase and the offline phase. So as it can be seen during the offline phase, you have devices at required points, which are locations that we don't know, we know. And we have a device, another device that collects this information. So we just simply collect, I'll show you the information that we collect in the next slide, but it includes the SSID, the MAC addresses, and the RSSI of the devices at known locations. So during the offline phase, we know the exact location where these devices are. So this information is then taken and stored inside a database on cloud. So the online phase, at this point, we're going to perform simulations. It will not be a real-time, we did not do real-time experimentation. We did the simulations. So the offline phase, it was the real-time experimentation. So this is the system itself. As you can see in the nav bar, we have the offline phase, which is the calibration phase or the training phase, and we have the monitoring phase and the navigation phase. Then we also have the share and the logout. So the monitoring and the navigation, they fall under the online phase. So what you do when you start with data collection or data generation, you need to start by clicking the offline, then you specify the location of the device that is tracked, or the device that is broadcasting its signal. Then you click the off button so that you can start with the calibration phase. So this is the kind of data that we collect. So once you start collecting, you'll see that you have the SSID of the device, the MAC address, and the RSSI, and the required point. So remember that I said that during the offline phase, we know the exact location. So during the online phase, we'll be predicting, based on the RSSI that we receive, we'll be predicting whether the device is in these locations. So experimentation and results. Our experiment environment, it was done in a building that has a dimension of 9 meters by 10 meters. So the building consists of 5 rooms, named room 1 until room number 5. And all the dimensions of the other rooms and all the material in the rooms that may interfere with the signal are also indicated in the diagram. We have, for example, the wooden material, we have microwave, we have fridge, all of these things that can affect the signal. So we start with our scenario number 1. So in the first scenario, we have selected 15 points from each room. And then from each point, we have collected 6 measurements. That means when I talk about the measurements, these are the measurements that we talk about. So we collected the SSID, the MAC address, and the RSSI, including the required point from each required point. So we had a total of 90 measurements taken from each room. That gives us a total of 453. The reason why we have 453 is because of we created this system in such a way that whenever it detects that there is a change in signal, it should automatically update itself, or it's user controlled, or it can control itself. So these are the results of the first scenario. We have compared the Gaussian naive Bayes and the kernel naive Bayes. So we can see that if without correcting the RSSI measurements, the accuracy of the kernel naive Bayes was 37.8%, and the accuracy of the kernel naive Bayes was 44%. So this, as you can see, that is not good enough. So we then applied a filter. After applying a filter, we see a little bit of improvement. But once again, this change 64.4% and 68.9%, that is not good enough. So we had to now increase the size of the radio map. So in the second scenario, that's when we increased the measurements at each point from 6 to 10 measurements. And now we had a total of 150 measurements per room. And the size of the radio map was now 753 observations. So there is a bit of increase. And as you can see, even the accuracy, as the data set increases, then also the accuracy of the application was also increasing. So once again, we saw the same pattern. Without filter, the accuracy is low. But when we apply the filter, the Gaussian naive Bayes increased from 50% to 50.7% to 70.7%, which is a 39.4 percentage change. And the kernel naive Bayes from 53.3% to 76.0%. So which is a 42.6% percentage change. So once again, the results are not, we were not happy with these results. So we decided that let's see what happens if we increase the number of, or the size of the radio map. Then we went to the third scenario. When we got to the third scenario, what we did, we said that at each point, we are going to now increase from 10 observations per point to now 14 observations per point. This now gives us a total of 211 measurements that were taken in each room. And the radio map size now has increased now to 1,054 observations. So without a filter, once again, the Gaussian naive Bayes was not doing okay, but the kernel naive Bayes, it was also not doing okay. But now check when we applied the filter. This filter, we have presented it in the previous paper, which uses the mean and standard deviation to filter the RSSI measurements. So if you check now, we see that the kernel naive Bayes has increased from 49.5% to 95.2%. And this is a percentage change of 92.3%, which at this point, we thought that these results, they were good enough for this point. So we moved on. The conclusion here was that the kernel, the data that we collect is more suitable for the kernel naive Bayes. So that was not all. So we had to now check, because we could not continue collecting data without knowing the destination. So we decided that let's take our data that we collected, the 1,054 observations that we collected, and now compare it with the data that was generated by another system. So it was generated by these guys in another study, and they had 56,099 observations. But when we now check the kernel naive Bayes that we selected as the best performing in our data set, remember that it has produced 95.4% accuracy. So we applied our filter, and we see that with this number of observation, the accuracy was 94.5%. So at this point, okay, I'll explain more as time goes on. But you can see that we did not know to what extent do we now say that the data set is good enough. So we had to make sure that the decision that we take, that the kernel naive Bayes is the best performing for our data. We have to verify that it is indeed the best performing machine learning algorithm or classifier. So what we did, we compared now the kernel naive Bayes, the Gaussian naive Bayes, the fine tree, the weighted KNN, the medium Gaussian. So we applied our filter. Then we see that in almost all the cases, you can see that our filter option was performing better in all the algorithms, except for the fine tree. So in the kernel naive base, with our filter option, we had 95.2%, and then with the Gaussian, that is the it was the lowest with 76.2. Then the fine tree is the one that performed better than the kernel naive base, which had 96.2%. But all these others, you can see that the medium Gaussian SVM, it performed the same as the kernel naive base. We also compared as well we applied other filters just to see whether our filter is also a good option for us. So we wanted to make sure that before we develop the online phase, we know exactly what results we will expect. So, but you can see that even for the median 3- which was applied by another study, the moving average, the exponential smoothing, you can see that our proposed filter was performing better in with the kernel naive base with 95.2 as compared to the 92.4 for the median, the 54.3 for the moving average, and the 56.2 for the exponential. So this told us that it actually matters the type of filter that you apply on your radio map. So yeah. And then in conclusion, I don't know what happened. Okay, in conclusion, we concluded that both the radio map size and the filter that you choose, they actually affect the accuracy of your indoor localization system. And then in future, we seek to investigate what constitutes radio map to be too small or too large in order for a classifier to maximize its performance. Thank you. If there's any question, then I'll take those questions.
Okay, thank you for the presentation. Let's see. Is there any questions? Okay. I stopped sharing now. Okay, so is the problem with the YouTube link solved?
Sorry?
No, I'm just kidding. Okay, so I'm moving on to other presentation. Like the other presenters are not here, so I'll move to the last one, the virtual presentation. So Luigi or Mattia, who is going to present? Please unmute yourself and inform me. Thank you.
Okay, hi everyone. I'm Luigi, and together with Mattia, we are both authors of this paper, but I'm going to present it. Can you hear me? And I share my screen.
Yes, we can hear you perfectly.
Okay. Okay. Can you see the screen?
Yes, we can see the screen.
Okay. Thank you. Thanks. Perfect. So good afternoon, everyone. And I'm going to present this work on behalf of my colleagues of both our University Politecnico di Milano and Francesco Canali, who is the director of the activities of the restoration activities at the Cathedral of Milan. And the title of our presentation is the monitoring of the Cathedral of Milan, an archive with more than 50 years of measurements. Brief introduction about the Cathedral of Milan, that we usually call Duomo di Milano. It is one of the biggest cathedrals in the world, among the first 5, and it seems all made up of marbles, but the construction materials are also bricks and mortars. It is a very complicated monument with more than 3,400 statues, many bas reliefs, characters in 55 stained glass windows, more than 100 spires, 96 gargoyles. And it's the symbol of Milan. All the people that go to Milan go and visit the cathedral. So this is the main construction material. It's a particular kind of marble that comes from Candoglia, that is a municipality rather close to Milan. This is a nice material, especially from the aesthetic point of view, but this material has problems of conservation. This marble is not eternal, so I'm going to show what are the main activities that are carried out almost every day to conserve the monument. An important aspect is where this material comes from. There is a quarry, and the marble of this quarry can be used only for the Cathedral of Milan. And this started in 1387, and still today, the marble of this quarry can be used only for the cathedral. The marble is not eternal, so every 6 months there is a visual inspection by a specialized staff of Veneranda Fabbrica del Duomo, that is the organization in charge of all the restoration and also maintenance activities in the Duomo. So every 6 months there is this visual inspection of all parts. As you can see, it's not easy. You have to become a climber for a part of these activities, and there is this inspection of every single piece of the Duomo. But in this presentation, I don't want to describe the normal maintenance. I just want to talk about what happened about 50 years ago, when the situation in the cathedral became critical. There were extensive damages to the pillar. And starting from that period, a monitoring system was installed in the cathedral, and this system is today still operative. Of course, it has changed over time with new improvements, but we are lucky to have an archive with more than 50 years of monitoring measurements. So the causes of the instability in the 60s were different. There were architectural solutions adopted for the construction of the lantern. So the big spire on top of the Duomo was added later, adding extra weight on the structure. So the materials are heterogeneous. But probably the most important factors that caused the major instability of the cathedral was caused by humans, with the extraction of the water from the ground in the city center of Milano. Water was important, was used in fabrics, so for the production. There was the extraction of a large amount of water from the subsoil, and this changed a kind of natural equilibrium that was there since several centuries. And so this caused a subsidence of the entire city center of Milano. We have some measurements performed between 1950 and 1970 that shows that the entire city center of Milano, that is about here, moved off about 22 centimeters. This is a rather constant displacement of the entire city, but in the overall displacement, there are also local small displacements that affected the the columns of the Cathedral of Milan. So several cracks were found. There was a major issue related to the stability of the cathedral. The first interventions were carried out just to, let's say, add temporary structures around the columns. And then after about a period of study of 15 years, a restoration of all the columns of the cathedral was carried out, replacing the most damaged pieces. In those years, in 1961, the first version of the monitoring system was installed inside the cathedral and was able to capture the vertical movements of a series of columns along the transept of the cathedral. These columns 85, 84, 74, and 75 are the biggest columns, and the spire of the cathedral is built on top of those columns. 28 is an external point, and it more towards the facade of the cathedral, and point 39 is the historic reference, is another point on a column that is used to compare all the relative measurements of the columns. In this historic graph, you can see a representation of the differential movements between the columns. Some columns started moving down, and some columns apparently started moving up. Actually, there is no movement in the up direction. It is just that all movements are measured with respect to this point 39, and so it appears that some points are moving in one direction, some columns are moving in one direction, and other columns are moving down. But it's just the effect of a relative representation of the displacement. After a few years, in 1969, this system was revised. Several other monitoring points were added inside the cathedral, and this is the configuration that is still available today. So starting from 1969, 1960, it was possible to measure the displacement for a large number of columns. Measurements were initially more frequent. There were measurements taken every season. Today, we still take measurements, but only in 2 seasons, always in the months of May and November. And we can produce this kind of representation from the 70 to 2020, where you can see that there were major movements in the period 1970-1980, and then all the displacement becomes more horizontal. What happened was there was the restoration of the columns, and in addition, it was decided to stop the extraction of water in the city center of Milano, and this immediately resulted in the change of the slope of the curves of the different displacements. In this color representation, you can see say a kind of interpolated map of the displacement, where it shows that the point with the minimum value is reached towards the south side of the cathedral, especially in the area of the transept, and this is where the 4 biggest columns are located. So the leveling network is not available only inside the cathedral, but also outside there is another one, 92 points installed on the external walls of the cathedral, plus some points in the square and along the main streets in the city center of Milano. These measurements are also still taken today, and with a frequency of 1 measurement a year. But the monitoring system of the Duomo di Milano is not only made up of these 2 leveling networks. There are several other systems. For instance, starting from 1972, some methods were added to measure the inclination of the columns, or there are also automatic methods to measure the movements of the spire. This is a kind of representation of the daily movements of the spire of the Duomo. And some systems were temporarily installed during some conservation activities. For instance, for the restoration of the main spire, a scaffolding was installed on top of the roof, and one of the requests of the engineers was to know the relative movements between the spire and the scaffolding, and some GPS were installed, one on the scaffolding, one on the spire, and there is another one that is external that was used as reference. So the topic of this presentation is not to present the entire monitoring system of the Duomo that is rather big and complicated, just to say that it started about more than 50 years ago. Several other sensors were added. The connection of the new measurements with the old measurement is possible thanks to the continuous maintenance carried out to preserve the monitoring system. And the latest system installed is a complete automatic one that doesn't substitute the existing ones, but is an additional integration, and it is made up of a series of tiltmeters, inclinometers, and accelerometers. So in this case, measurements is not carried out every 6 months, but is continuous measurements 24 hours a day. To conclude, I have just briefly introduced the monitoring system of the Cathedral of Milan, made up of several sensors. First measurements were taken more than 50 years ago, and it is extremely important to have such archive and to continue taking measurements, because in only in a few historic buildings there is availability of data going back to more than half a century. What we do today is to go there to continue taking measurements, and every 6 months we produce a report with data, graphs, schemes, a description of the system, the observed movements, and all this is carried out in collaboration with the staff of the Veneranda Fabbrica del Duomo, and our aim is to preserve the most famous monument of Milano. New sensors were installed in different years, so technology changed, but we still keep the traditional system because it's fundamental. And the collaboration between our University Politecnico di Milano continues with Veneranda Fabbrica del Duomo, that is the historic organization in charge of all conservation activities. So thank you very much for your attention. I think I can stop sharing.
Thank you for the presentation, Luigi. Is there any question for Luigi? Not from on-site people, and no online as well. Okay, I think this is fine. Thank you. Sorry, are you the next presenter? I don't know. Okay, so the other presenters are not here, so then I close the session. Thank you for the presentations, everyone. See you. Bye.
Bye.